Okay, let's go through a couple of Rust reports first. Microsoft is now treating that as a first-class language in Visual Studio. They also have done some device RAID API in Windows. Again, security and improvements of speed. Ventura is the new Nginx replacement by Cloudflare. They also state it's only taking a third of the CPU resources now. And they also say Nginx was purely for C, and even for experience engineering it was really error prone. Google stated there are 0 memory safety vulnerabilities in their Android Rust code, and they are increasing the Rust code significantly. Even Linus is now accepting a new language in Linux. So what we see is a couple of terms like security, performance, memory safety, saving resources. The question is why? Well, there's 3 core concepts. That's the move semantics, the ownership tracking, and the borrow checker. Let's go through them. First of all, just a bit of a memory model what we have. We have registers, the very close things on a CPU, then we have the stack. Both are usually once per thread, at least virtualized. And then we have the stack, the static memory, and the heap. We will currently not talk about static memory. Obviously, that's also an interesting topic, but not for now. And registers on the other side, they're not accessible in Rust. And by the way, they're not really accessible in C as well. That is mainly an illusion. There is another level what we have, the yellow one. We have the names in the source code for humans and for the compiler. They don't take up space, at least not on the target. Then we have the stack, pretty commonly in C, C++ and other languages as well. That's where most variables are used and stored. As we said, we don't talk about statics currently. And then there is the heap. So the difference between a stack and the heap is static is kind of a compile time layout. It's kind of static. Obviously the calls and how they are called, they are runtime dependent. So how to stack them on top of each other is really runtime, but the layout in the stack in one function is a static compile time. Whereas the heap is completely dynamic. It's a completely runtime behavior. This is C, C++, and Rust, and other languages as well. Memory leak definition is if the name in the language and also the pointer to it, which is often on the stack, goes out of scope and nobody is pointing to that data on the heap anymore, but it's still in the heap, then we have a leak definition. Leak means there is a free memory leakage because the memory is still blocked. There's one concept we only have in Rust. Variables may be uninitialized, but in contrast to C or C++, this means memory is not assigned to it. Whereas in C, C++, memory is there. It's just not known what is in there. Okay, let's move through a bit of Rust examples. Let's start here. We define a struct. We will use that later on. This is very simple struct to demonstrate some things. And then we assign a variable, a with the type u8, and assign it to 7. And what you see is here you can see the code pointing to the stack where the variable is located at. It will be just gone when the block is left. And the same applies for B. We can do a lazy initialization, but that's not important here. The interesting thing is now the red block, since what we have here as a string is a string holds is metadata, management data on the stack, at least in this case. And the dynamic part, the content of the string, not the length, is on the heap. And the string class makes sure that if this one is out of scope, this one gets deleted as well. The more general concept is the box. So this one is kind of a sequence of characters what a string has. This one, a box can be put on every structure and even on a unsigned int bit int. So that's what you can see here. T is pointing to a box, and the box is essentially pointing to this data element here. Okay, that's it. There is a couple prints. We assign the structure here as a point to E and do a couple stuff with it. That's all. We will see these things later on. Okay, now let's talk about move semantics. Again, the same application what we have here. We see the same thing what we have done before. Now we add element E. So we assign E a point, which we have done before as well. This is a structure here. And then we move E, the content of E, to F. We are assigning a new variable, which means in Rust, it's not a copy, it's just a new assignment. So after this, E is really not pointing to anything anymore. It's uninitialized. Whereas F is taking the variable as it was before on the stack. You can see this really in the error message of the compiler. There is a movement going on, what you see here. And that's what we tell here. Value is moved here. If we want to print out E, that's the compiler message. It's not there anymore. You can't access it anymore. But the compiler is pretty good in telling that. Remember, if we do this, it's always a move, except if the type has the copy trait. Okay, the next concept. That's the ownership tracking. Ownership rules means each value has an owner. There has to be an owner. And there has to be only one owner at a time. And values get dropped, uninitialized, freeing the space, when owner goes out of scope. We can even manually drop variables. There is a call to do that. Okay, let's take an example on that. What we have is, again, we have the let f equals e, and we have let c, which creates a string. If we take that, what we have seen before, we move really that ownership of the content of this one from one variable to the other. And we can assign things here to the string. So nothing new on that. So that's about it. What if we see it on C and C++, if we really think about the heap management now, what we see on C and C++, if we find this, remember, as a memory definition, this goes out of scope, but this is still there. If the memory name is out of scope and the stack is also freed, you have to do a manually free or delete, or put it as a pointer to some other structure which is still there. So otherwise it's not accessible anymore. So the programmer is responsible for inserting free or delete. If we take the same on Python or Java, just on those garbage collector languages, we also let this one go out of scope. But there is somebody underneath. It's called a garbage collector, which checks if there is any reference left here. And if something does not have any reference anymore, it could be freed up. There's also in C++ and other languages like Swift, the smart pointers and automatic reference counting. They are really helping, but they have also a bit limitations and obviously a runtime overhead. Rust, on the other side, has exactly the same thing as C and C++, because we need to delete. There has to be an explicit delete call. But the difference is Rust is inserting that automatically. So you don't have to manually do that. And it's not done by a garbage collector at runtime. It's due to the type system that the compiler can insert those calls which you have to manually insert in C++ automatically. And always. So the borrow checker is another key concept. At the very beginning, Rust was pretty much like Go. And as Go was introduced, there was also thinking about, well, Rust is just another Go, so what is the purpose for that? But that was about the time when Nico Matsakis came up with a new idea, what he called borrow checker. You can read that here. That's really interesting, I have to say. But you probably have to read the whole history then. Let's see. Let's take a look into that. What we have is references means borrowing. You know the concept of references probably from other languages as well. It's kind of, there is still an owner, but you borrow the book. And the interesting thing is, on those languages, you can even borrow one book to 2, 3, 4 readers, but not multiple writers. We will come to that. Okay, what does borrowing mean, or references? That's the reference sign, the same as C++. So what happens is that E is still pointing to that structure, which you are familiar with at the beginning. But F is now pointing to a data structure, in that case on the stack, because we have assigned it on the stack. And there is a reference structure which points to the original data back. So that's all about referencing. So what is the borrow checker now doing? Because the borrowing follows rules. At any given time, you can have either any number of immutable references. That's what I said. You can borrow a book to 5 persons at the same time. Kind of unusual for books. And they can all read it. But you can't do the same with 1 or 2 are writing to the book, or more than 1. So you have any number of immutable reference and 1 mutable reference. Well, maybe we have to introduce the mutable. Regular variables are kind of constants. You can assign them once. You can assign them a second time, but that will be shadowed. I'm not talking about that now. But they are usually constants, one-time assignments. And then you can create references here. So F is a reference to E, but also const, immutable. And this works pretty well. So what we can do is we can assign those 2, and we can also print out all 3 variables, E, F, G. They are all pointing to the same data element, which was created here. So if we do exactly the same here by creating a mutable object, and that's the key element, create a mutable reference here as well, at the second time, the compiler complies. So let's check what they are talking about. So we are finding the error message of line 8. Second mutable borrows occurs here. So we can't do that. The first borrow later used was here was okay. So the compiler tells you pretty closely what is happening here. Obviously, a third thing is, which is important, references must always be valid. So references are no pointers. They are really references, again, pretty much the same as in C++. So together with move semantics, this really reduces data races a lot. Well, for the compiler, it has to track all that stuff. It has to know, when do I have a reference? When is the reference going out of scope? Which means if I keep that variable and those references are getting out of scope, I can add a new mutable reference again, because the other one was going out of scope, so the numbers are decreased. In order to check all that, there is the concept of lifetimes, pretty important. That's something you rarely see on the surface. But the compiler always has to treat with those lifelines, because otherwise the compiler can't tell you when things are decrementing the reference counting, or even incrementing as well. So what are lifelines? There is a special syntax that's always with a tick and a name. So that's what we have as a lifetime syntax. But as you see, there are lifetimes here involved, but you don't see it on the language level. So the age variable gets introduced here. And since the block ends here, the lifeline ends here as well. So this is the lifetime of the variable age. You could have added that as tick A here. For year, it obviously started here, and since there is a block, year ends here. So this would be the tick B lifetime. String is again in the main block, but introduced a bit later, so it will just be at the end of that. And so on. Sometimes you have to give the compiler, especially on function calls, the hint that which lifeline will be the resulting lifeline for the return argument on a function. So that's why sometimes you see such constructed where the lifeline is in there, oh, this tick is wrong, the others as well, that we have the arguments and the return value really have assigned a lifeline so that we can see, okay, if an argument 1 has this lifeline and B has this lifeline, we know the result have either one. That's just a hint in the compiler, but normally it's not really required to do. So, summarize the heap management. What do we have in pros and cons? If you have garbage collector, it's pretty error-free, at least on the memory management. And we do a pretty fast coding. That's what we all see, especially in Python. I love Python. But we fully don't have any control over the memory in Python. It's really a kind of unpredictable runtime. We don't know whenever the garbage collector kicks in. And also the program size gets larger because there has to be some code, there has to be some thread in the background running on with the garbage collecting. Always those variables have to have references on all that stuff. On the other side, we have C and C++ with the manual memory management. We have full control over memory. And the runtime is pretty fast, as we all know. And we have a small program size. That's why I use it in system programming. But it's really error prone. If we forgot such thing, we have a problem. Coding is therefore way slower because we have to think about an aspect all the time which we don't have to on the other approaches. And it requires a lot of testing. And there is the ownership model of Rust. And it might not be only part of Rust, it might be in future languages as well. We really have full control over the memory. Not in a sense as C++, but enough for what we need usually. It's a very fast runtime. Usually, so Rust is even faster as C++, pretty often. And we have a small program size. Still the same as a C++. But there is slower coding. And there's really a steep learning curve. But what you get here is still the benefits of fast runtime with the error freeness. Well, almost. Obviously not complete. So if we take a look on what is very essentially detect bugs. In Rust, we detect bugs really very early in the development. That's what is really annoying because bugs in the development means there's error from the compiler. So we get a lot of errors from the compiler and the compiler is really picking, and that's really annoying, I have to say. But if we really make a product at the end, we will see that later on stages, we don't find that many bugs anymore. Even in testing, we get less bugs. But especially later on, there is a fair chance. Remember the statement for an Android? 0 bugs found? Well, that will not stay there, I'm sure. But the problem is, at the very beginning, it's a big step and it's a steep curve to do that.